Hello, welcome back to Chapter 1, Part 3 on falling objects. Any discussion of falling objects would be incomplete if we didn't talk about the contributions of the great scientist Galileo. He's considered to be the father of modern science. Galileo was about understanding nature based on evidence, experimentation, and observation. This is something that was not done before Galileo's time, and we sort of take this for granted today that this is how science is done. But Galileo is generally credited with starting this type of analysis of science using evidence and experimentation. Galileo viewed the laws of nature as mathematical, and he basically was able to separate science from other ways of looking at the world around us, such as philosophy and religion. So this was a huge leap in human thought and a huge advance in our progression to understanding the natural world that we live in. Galileo was extremely resourceful. Without the advantage of having technology such as clocks available, he sometimes used his pulse as a clock for experiments involving motion. Galileo was probably most famous for using his telescope to advance astronomy. He discovered that the sun had sunspots, which was not supposed to be the case because all of the objects in the heavens were supposed to be perfect. Galileo studied the moons of Jupiter and realized that these moons of Jupiter were orbiting around Jupiter, just like a tiny version of our own solar system. This proved that not everything revolves around the Earth, which was thought before Galileo's time. Galileo also studied the phases of Venus as Venus made its circuit around the sun, and this ended up being proof that the sun was in the center of the solar system and not the Earth. So Galileo, the experiments and evidence that he collected and observations basically allowed the heliocentric model of our solar system. In other words, having the sun in the center of our solar system. This model could now be advanced because we had proof for it. However, his views didn't sit well with the Catholic Church, which had a lot of authority and power back in those days, and so the Catholic Church actually placed Galileo under house arrest until his death for his radical ideas. For this part of our lecture, the work of Galileo is all about falling objects. Galileo was famous for doing experiments with falling objects, supposedly using the Leaning Tower of Pisa to drop stuff off and take notes and record his findings. So Galileo discovered that all objects, no matter their weight, shape, size, or composition, fall at the same rate. Now, one thing we have to be a little careful of when we say this is we have to be able to choose objects such that we can avoid air resistance. So, by the way, this is when we drop objects or have objects falling such that they're under the influence of gravity only, this is called free fall. You can enjoy the videos that are coming up next where I'll do a bunch of experiments similar to what Galileo did. Unfortunately, I will not be traveling to Italy. I'll be doing them in my backyard. Nonetheless, we can demonstrate a lot of the findings that Galileo saw. So please enjoy the videos.
Our first test is a tennis ball and a 5-pound weight. Our next test is a tennis ball and a 20-pound weight. This test is a 20-pound weight and a light wood block. Hello again. When we do these experiments, we have to be careful about air resistance, also called drag. So let's try doing an experiment here in the garage where there's no wind And let's drop a heavy book and a coffee filter. What do you predict will happen in this experiment? Here we go. All right, I'm guessing you were right. And the coffee filter, of course, fell very slowly because of wind resistance pushing on it. Can you think of any ways we can reduce the wind resistance? Well, there's a couple things we can do. The first one is we can reduce the surface area of the coffee filter because that's where the air is pushing on it, creating that wind resistance. So if we crumple it up into a tiny little ball, now we have the same weight, but much less area, so we've reduced the wind resistance. So let's redo our experiment now and see what happens. It's going to be a little hard to see the coffee filter now. But as you can see, they both fell at the same time. Now there's one more way that we can reduce the wind resistance. We can place the coffee filter on top of the book, like this. And what that'll do is the book will actually block the wind that's striking the coffee filter to reduce the wind resistance. Let's see what happens here. You can see that the coffee filter dropped just like a lead weight. Thank you.
So Galileo discovered that not only did objects fall together at the same rate and hit the ground at the same time, but that all falling objects accelerate as they fall. In other words, when you drop something, it speeds up as it falls down. So all objects have the same acceleration due to gravity. So this is a very important number, this acceleration due to gravity. And so we're going to just call this G for gravity. So again, let's do some experiments. We can do an experiment to actually measure the acceleration of gravity, g. So let's start with the distance formula. Remember from the last part of this chapter lecture, we learned that the distance that an object travels, d, is equal to 1/2 at squared. And a is the acceleration of the object, and time is how long the object accelerates. So this is easily, we can easily modify this equation for a free-falling object by just setting a, the acceleration, to our new acceleration, which we call g. So the free fall distance formula looks like this now. Distance, that means how far something falls, is equal to 1/2 g t squared. And what we're going to do is a little simple experiment and just try to get an estimate of what this value of g is, because this must be an important number since every object on Earth falls with the same acceleration. So what we can do here is take the distance formula and simply solve it for g. So we can multiply both sides by 2 and divide by t squared, and we get g is equal to 2d over t squared. So in the experiment, what we're going to do here is I'll drop an object, a ball, a distance of 2 meters. So my distance here will be 2 meters. And then I'll use a stopwatch and try to, as best I can at least, measure the time t that it takes to fall. And I'll use an average time. So I'll do several trials and take an average, and then we'll get an estimate for g. So again, please enjoy the demonstration where we attempt to gather some data to calculate g.
Okay, in this experiment, we're going to drop this tennis ball from a position right here marked by this tape that's exactly 2 meters from the ground. And we'll time it, and we'll take a series of measurements here to see how long it takes for the ball to drop. So I've got my stopwatch on my cell phone here. Let's do some experiments here. All right, our first experiment, the result is 0.61 seconds. .66. 0.63.
Okay, so in our experiment, remember that what we did is we solved our distance formula for g, which is 2d over t squared, and I dropped the object 2 meters. I dropped the ball a distance of 2 meters, and I did 3 trials, and the times I got were 0.66, 0.61, and 0.63 seconds. I can average those together. I can add them together and divide by 3, and the average time is 0.633 seconds. So let's plug in these numbers and see what we get for g. So remember, our distance d again is 2 meters, so there's our 2. And our time t is 0.633, and we have to remember to square that. So on top we get 2 times 2, which is 4, and on the bottom we get 0.633 squared, which is 0.401. So this number here, 4 divided by 0.401, gives us a value of g. Our estimate of g is 9.97 meters per second squared. So if we round this to 1 decimal place, this rounds to 10. So our estimate is 10.0 meters per second squared. It turns out that the actual value, if you do this experiment, using much better equipment and so forth, the actual value for g is 9.8 meters per second squared. But you can see our number is very close. This is only a 2% error, meaning 98% accuracy, just by doing our simple and quick experiment by dropping some tennis balls. Before we move on, it's useful to think about, in terms of experimental physics and how to set up an experiment, how could we improve this experiment that I did so that we got a more accurate value? How could we get our error, down to just a tiny fraction of a percent? Well, there are a couple things we could do. We could use a higher drop. In other words, instead of just using 2 meters, maybe increase it to 4 or 5 or even 10 meters, something like that, as long as we keep wind resistance out of the picture. And then by far the biggest part of the error came from my using a stopwatch by hand. Obviously there's a lot of error there with my reaction time and when I press the buttons and so forth. So using some sort of electronic timing system would certainly get us a much more accurate result. Okay, so the key thing here is that the acceleration due to gravity is given by g equals 9.8 meters per second squared. So this is the number that we're going to use for the remainder of this course whenever we need to use the acceleration due to gravity. Now, one thing we should just keep in mind here, that this is a special number, but it only applies for here on Earth. Since gravity is different on different planets, for example, on the moon, gravity is about 1/6 as strong as it is here on Earth. So g is only about 1.6 meters per second squared, meaning if you drop an object on the moon, it will accelerate 6 times less than it does on Earth. It'll look like it's falling in slow motion. However, on a planet like Jupiter, where the gravity is much greater, g is 23 meters per second squared. And if you were able to stand on the surface of the sun, certainly you can't because the sun does not have a surface, and it's also about 6,000 degrees Celsius. But if you could do the experiment there, you would find that g has a very high value of about 274 meters per second squared. So let's finish up this section of the lecture with some free fall word problems. So suppose a bowling ball falls from the roof of a 100-meter tall building. So here's our picture here. We've got our building, and we're going to kind of set up this coordinate system here. We're going to be working here, in this vertical direction. So the top of the building is at a distance of 100 meters from the ground, which is at 0 here. And we're going to have a ball that starts up here, and it's just going to fall from the building and smash down below onto the sidewalk. So the question, first part A, says, how long does it take to hit the ground? So what we want to do here is use our distance formula. Remember, for a falling object, we have d equals 1/2 gt squared, and solve for t. So doing a little bit of algebra here, multiplying by 2 and dividing by g and taking the square root, we get t is equal to square root of 2d over g. The distance is 100 meters, and g, remember, is 9.8. So we have 2 times 100, which is 200, divided by 9.8, and then we take the square root of that result, which gives us a time of 4.5 seconds for the bowling ball to hit the ground. Part B, how fast is the bowling ball going when it hits the ground? Well, remember that we learned earlier in this chapter that the final velocity of an object is equal to the initial velocity plus the acceleration times the time. Now, we can use the same formula here. The only thing we have to do is we have an object in free fall. We know the acceleration, a, is equal to g, which of course is 9.8. So let's rewrite our equation here as final velocity equals initial velocity plus gt. And of course, the initial velocity of the ball is 0 because we're dropping it from rest. In other words, the instant we let it go from our hand, it hasn't started moving yet. So its initial speed is 0. So we have g is 9.8, and t, the time we calculated here, was 4.5 seconds. So 9.8 times 4.5 is 44.3, and the units come out to be meters per second. Part C, how far does it fall during the first 2 seconds? Okay, so remember, it takes 4.5 seconds to hit the ground. We want to know how far does it go during the first 2 seconds of it falling. So again, we're going to use the distance formula. Distance is equal to 1/2 gt squared, and all we're going to do here is plug in g, which is 9.8, and the time here, t, we're going to set that to 2 seconds. And remember, this 2 is squared here, so this is actually 4 times 9.8 times 1/2, which gives us an answer of 19.6 meters. So what that tells us is that the ball falls about 20 meters, right? 19.6 meters, which would be maybe about right here in this picture. That's how far it has gone after the first 2 seconds. So that concludes our lecture here on free-falling objects. I will see you for part 4 of this chapter soon. Goodbye.